Welcome back, students, in this new lecture from unit number 2. This is Avinash Panchal delivering the lecture on this 1D analysis of bar. So now we see next problem which is given in on the screen. So here we have this problem. Determine the support reaction forces at the two ends of the bar shown above. Give the following, that is given P, that is load, point load which is acting at the center of this bar is 6 into 10 to the power 4 Newton. E is given, that is Young's modulus or modulus of plasticity is equal to 2 into 10 to the power 4 Newton per mm square. Area is given, that is throughout same cross section area is present, and it is equal to 250 mm square. Length of the bar is 150 mm, and the allowable deflection is 1.2 mm. So in this problem we have the bar is having area 250 mm square, and it is fixed at one end and restricted at other end by 1.2 mm. So what this problem is showing over here, that there may be deflection because of the point load P. There may be some sort of deflection, and we have to just determine if the deflection is more than the allowable displacement, that is 1.2 mm, then there may be some type of compressive stresses will act on the bar, and because of that forces there may be some stresses inside the bar because of these restrictions. Also we have the value of 1.2 mm. If it is less than the actual free expansion of this bar without restrictions, then what we will do, then we have to consider this as a delta 3 or u3, or what we can say the displacement at node number 3. Okay, so if it is that is allowable displacement is less than this 1.2 mm, then we will see that there may not be having any effect of these restrictions. So we will see the further solution of this problem. So first we will check there is the contact of the bar with the wall on the right, that will occur, and we will simply find the effect of this load P on this bar, and we can find the deflection at node number 3. So entire deflection in the bar that may be calculated with the help of the simple relation, that is PL upon EA, and by putting all the necessary values we got the value as 1.8 mm, and it is greater than the allowable displacement, that is 1.2 mm. So now we will find the element stiffness matrix first, that is K1. Okay, and is equal to, we know that AE upon L into 1 minus 1 minus 1 1. So if we put these values, and these are corresponding elements for this node 1 and 2. If it is for element number 1, then what will happen, it is correspond to node number 1 and node number 2. So these values are also corresponding to node number 1 and 2, node number 1 and 2. Okay, so if we consider k2, it may become a e upon l into 1 minus 1 minus 1 1, and which will be corresponds to node number 2 and node number 3. So it will become node number 2 and 3. Also it will become node number 2 and 3. So what we have to do for combine or global stiffness matrix, then there are three nodes for this problem. So the order of global stiffness matrix, that will be 3 by 3, and we can find this A upon L as a common, because there is a similar area, similar length and similar Young's modulus is applied over here. So only the change will be the matrix. So here this matrix is having the value of k1 and this one is k2. So here this 2, that is central element, that is a second diagonal element, which is applied given as 2, because this value of k1, the last element of k1 and the first element of k2 both will get merged, because these are corresponding to the node number 2, so that it is added and other values will be kept as a same. Okay, so now we will have the next slide. So here we can see the boundary conditions, that is force is applied at node number 2, so that is F2. So here we have U2, that is displacement at node number 2 is always 0, because wherever there is an deflection, or what we can say, wherever there is, we are considering the deflection at a fixed point, it is always be 0, because at fixed point there not possible for any deflection. So we will consider that as 0. So we have elimination approach. So because of this 0, this row number 1 and column number 1, that will get 0, and what is remaining over here is this 2 by 2 matrix. So with the help of this matrix we can find the equations, that is E upon L into 2U2 minus 1 into delta. Delta is given as a 1.2 mm, because it is allowable. Beyond that there will not be possible for a deflection, so that we will take it as a 1.2 and is equal to p, that is what, 6 into 10 to the power 4. This is equation 1. Equation number 2, that is E A upon L into minus U plus 1.2 and is equal to F3. Okay, so then we will find F3 is equal to 0, because no force is acted over there, only reaction forces will be considered for that. So F3 is equal to 0, we will consider at a 0, so that by finding or by Solving this simultaneous equation, we can get the values of u2. Okay, so we will get the value of u2, and we have this value, that is 1.5 mm. So here we can have this value of u1, u2 and u3. So what is remaining over here, we will go to next slide. So here we have to find just this support reactions, and we will apply the first and third equation for global Fe equation. So first one we will give for the force. So we can have this first support reaction, that is F1, or what we can say, we can take it as a R1 and this is R2. So we have this formula for this. So here we can have the value of this third element is 0, because we are considering the reaction at support, or at node number 1, at support or node number 1. So for that we will consider that as other elements as 0, because only node number 1 and 2 are active with this. So by calculation we will get this value of minus 5.0 into 10 to the power 4 Newton, and F3 similarly we will get, that is R2 reaction at node number 3, and it will become 1.0 into 10 to the power 4. So we can easily find these values with the help of given procedure, and it will be beneficial for finding any type of problem. So thank you very much.